started the recording. Let's wait another minute, let's say. I still see people that are joining. Okay, so let's start. Again, we will record it so people that couldn't join or different time zone, that's hard to join, they can watch it later. I have Phuong and Sudhakar with us from NVIDIA to introduce you the LLM task that we have for the virtual teams. Phuong and Sudhakar, go ahead.
Okay, yeah. Hello, everyone. And today we will give you a quick introduction to the LLM task for the virtual competition only. So for the on-site task, we will have another task that we will publish more information later, but note that this is only for virtual competition. So we have two judges for this task. My name is Phuong, and I'm a senior performance engineer at NVIDIA. So in the past, I did my master in Technical University of Munich in computational science and engineer. And I participated at the student cluster competition at ISC 19, SC 19, and ISC 19. For daily tasks, I'm working on optimizing large language model training with different precision, and also looking into computation overlap, and I'm running on caffeine and GPU cycles.
Hey everyone, my name is Sudhakar and I work in the same team as Phuong, senior performance engineer at NVIDIA. And I did my master's in computer science from North Carolina State University in Raleigh. And I debug LLMs on NVIDIA GPUs for a living, and would love to see all of you optimize some LLMs as well. Let me then quickly digress into why this matters. The problem is the scale. Before 2017, the models were smaller and you could just train them within hours on a single GPU. But after 2017, when the attention and BERT specifically, they exploded and transformers arrived, the models grew very fast. And it just seems like it is yesterday when we all started to use ChatGPT, and now the clouds are running our machines. And so in 2020 to 2022, we saw GPTs, Palms, which cost like millions of dollars to train them. And then after that, there was an explosion of Llama, Mistral, Nguyen, you name all the animals possible. Training them is still expensive. And more recently, last year, we had DeepSeek R1 that even sparked geopolitical debates, especially with compute efficiency. And it would be nice if we just had a single accelerator, enough memory, enough compute, and we just click run, and the model would train. But thankfully, it is not the case, and we still have our jobs. And so today's challenge is to make every GPU hour or accelerator hour count. We need better parallelism, smarter batching, less memory waste, and that is why we need efficient training of LLMs on our machines. For this competition, the stack that we are going to use is Max Text. It's a it's an open source LLM training framework by Google, and it's based on their JAX framework, XLA compiler, and it's hardware agnostic, so it can run on TPUs. For this competition, though, we are going to focus only on GPUs. Now, MaxText has a host of models that it supports, like Gemma, Quen, DeepSeek, Llama. For this competition, we are going to focus on Quen. We're going to talk about that in just a little bit. MaxText also has training techniques like pre-training, supervised, post-training RL, and also abstractions for scaling. Like different types of parallelism, data parallelism, FSDP, tensor, pipeline, context, you name it, using smaller precision like FP8, NVFP4, and also memory saving optimizations like host offloading, rematerialization, etc. And underneath, it uses JAX core libraries like Flax, which is neural network layers, Optax, which has optimization routines, AQT, which is the quantization or running in smaller precision, and Orbax, which is checkpointing library. And as I said, beneath all of it is JAX framework working hand in hand with the XLA compiler, and that makes it hardware agnostic. But for this competition, we're going to focus on running Quen in MaxText, specifically for GPUs. Now, I talked about Quen a little bit, but what is it? It's a very recent model from Alibaba Cloud. And we are going to focus on the Quen 3 14 billion parameters model, which is by the name has 14 billion parameters. The architecture has 40 decoder layers. And to just refresh what a decoder layer looks like, there's a diagram on the screen. We have an embedding which converts text to tokens that the layers can then process. We have RMS norm before the attention mechanism, then another RMS norm, and then a feed forward SWIGLU, which is an MLP. And then finally, we have an RMS norm, a linear and softmax, which just produces the next token from the context. As I said, 14 billion parameters, 40 decoder layers. It's Llama-like architecture, and it is trained in BF16 precision. For the purpose of this competition, we chose it because it's large enough that we can tweak things like scaling it on multiple GPUs or changing batch size or rematerialization. So basically, it is small enough for experimentation and big enough to test some of our training scaling hypothesis. So that is why we chose Quen 3 14 billion parameters model. Since it's open source, a lot of information is already available online. You can find different kinds of instruction or fine-tuned weights as well on Hugging Face. But Phuong is going to share later how you're going to use that model or model weights. Going on. Yes, so this is your supercomputer, Romeo. Before going to Romeo, I want to just quickly introduce what Grace Hopper GH200 superchip is. It's a Grace, which is a CPU, and Hopper, which is a GPU, superchip. They are on the same. They're on the same chip. It has 96 GB HBM3 memory, 900 GB per second NVLink chip-to-chip connection between CPU and GPU. And there is 4th-gen NVLink between GPUs. Now, this is just one GH200 superchip. On a Romeo supercomputer node, you will have 4 GH200s on one node. There are 58 such nodes. And the bonus task would be for you to scale it across multiple nodes. That is 8 plus GPUs. And if you have any question about any of these things, feel free to reach out. Now I'm going to hand it over to Phuong, who's going to tell you more about the competition.
Thanks, Sudhakar, for giving very detailed into Romeo supercomputer and the GPU architecture, because I think it is important to know the architecture well enough so that you know what to expect and what else you can optimize beyond your software performance. So moving on for this competition, so imagine that you will be an AI engineer and you want to optimize for the training efficiency for the Quen 3 model on a Romeo supercomputer. So the task will include two main tasks. The first task is to optimize the training so that you can have as high throughput as possible. But of course, the loss curve needs to stay stable without any nonce or spike. And then in the second task, you will have a chance to look into profiling to really verify your theoretical behind the training to see really what going on behind and what going in the correct manner, what go in the wrong manner, and what else can you optimize. And in the bonus task, we encourage you to try to train this on multi-GPU and see if you can achieve even higher throughput than the single node training. So we will provide you a converted model weight and also the data set on the shared folder on Romeo supercomputer. You simply can go there, check out the folder and fetch the model weight and the data set. So the model weight and data set are provided in this folder. So please make sure that you all have access to this folder and let me know if you have any issue. So for this task, we only ask you to follow a few instructions at follow. So first of all, you will need to run 5 full equal in this training. So by default, MathText will set a 150,000 steps, which is really high number of steps. But by setting the number equal to 5, the training will stop as soon as it finishes 5 equal, like looking to the data set. So the time step doesn't matter at all. You don't need to set it for the real training. So we ask you to give the max target length to 2048 at the common route for everyone so that we can have a fair comparison. The data set and the checkpoint, as I mentioned, it is provided in that shared folder. You don't need to do any conversion, just need to vector and start the training directly. And please watch out for the loss curve because we do ask you to plot that curve later, but please make sure that the curve decreases gradually to the 5 equal. So that no, doesn't matter which optimization you involve, you will implement and you will test to try, the loss need to increase into lower than 1.9. And the rest, you have freedom to explore whatever optimization out there in MathText. You can try different parallelism strategies. So given that you have 4 GPU, you can try different combination of them, not even single, but multiple of them in a combination way. You can try to increase the batch size by default. In the instruction, I give you the batch size of 1, but please feel free to increase it if you think it may have your throughput. And again, all the configuration that supported MathText, like materialization or activation checkpointing or any quantization like FP8, FP4, any attention like flash attention, anything. You have freedom to do anything to try or the optimization. And just please record the option that you go with and pass us the config file or the command line that you run so that we can reproduce it later, because all results need to be reproducible by us when we validate the submission. And then for this task, we ask you to collect the log file when you do the training. In the log file, it will bring out the loss per step. So we want you to plot that curve to make sure that it goes down gradually, so it doesn't spike up or become nonce. That is the first criteria to define that the submission is valid. And then for the most important thing here is that we will rate your submission based on the tokens per device, no, token per second that you achieve. So let's say if you have 4 devices, you can multiply this number by 4 because MathText only bring out a token per second per device. And make sure to skip the first 10 steps in the training because this is the warm-up phase. So you will see that performance will be up and down a lot. So it doesn't represent well the average throughput that you have. So we will provide you also a script to calculate the average throughput in case if you don't want to calculate by yourself. So all the instructions you can find in our wiki page. So for the second task, as I say, so I think it would be really interesting for you guys to look into the profiling and see what's going on with the training, what really happened underlying. So we prepare a set of 3 questions for you to answer, and you will need to list this in your report. So first of all, we want you to watch out for the communication pattern, because here you will have at least 4 GPU. So with different parallelism, there will be different communication pattern that you expect to see in the profile. So we want you to identify which communication happen inside of which step, and yeah, if you can map it into your parallelism stream, it should be great. And then also second thing, that it would be interesting to know whether the communication overlap with computation. So this is important when we do LM training, because you know, like if the model be really large and we need to distribute the model into multiple node or multiple rack, then the communication is always the really expensive part for us, and we want to make sure that the communication, whenever it can overlap, it will be overlap with computation, so that the GPU is not idle waiting for data forever. So it would be interesting to see if you manage to have this communication between computation and communication overlap in your profile, and if not, then maybe you figure out why. And the rest is tell us anything interesting that you find in the profile, anything that abnormal, anything that different to your expectation. We're happy to learn and discuss with you more on this. So on the right side, you see that this is a screenshot of the XProf program that we usually run with JAX or MACTEC program. It has pretty clear information on which layer the computation happen with what is the GPU device, what is the device kernel it's on, and then all the communication pattern grouped together in the forward pass and the backward pass. So there will be, so you can find information about how to run XProf in our instruction also, as well as online from the XProf or JAX repo of Google. And to run XProf, it's already supported in MACTEX. You only need to pass a configuration flag. So we also provide that instruction in the wiki page, so that you know how to launch MACTEX with XProf, as well as how do you open the XProf profiling. For scoring, as I mentioned before, so first of all, we need to verify that the submission is valid in a way that, first of all, it finished 5 equal and the loss is stable. So if you manage to have a submission which is valid, we give you 30 points. And for the throughput performance, with the 50 points, we will scale across the team in the way that the team have higher performance will get 50 points, and the team have lower performance will get 0 point. For the report, we expect to have a really short report, as short as possible. So we expect to see some analysis why you come up with that optimization, what do you think is better, and some answer for the profiling analysis. And if you manage to run it on multi-node, you will get a bonus point of 10. Note that we won't provide you any additional instruction or troubleshooting for this, because this is a bonus challenge. And as I say, the most important part before thinking about throughput is that the submission need to be valid. It need to finish 5 equal, and the final loss need to be lower than the threshold without any spiky or nonce in the loss. For the submission, we will try to make a folder on the Romeo so that you can upload the checkpoint, because the checkpoint will be around 25 gigabytes. We want to see the report and then some running logs. And if you want to modify any source code, please submit the source code there as well. For the tip, I would recommend you to check out our instruction. Make sure that before any optimization, make sure you will be able to run it first. The full training with the 6 million token data set that we provided by default will take around 2 hours. So I would recommend you to, for optimization process, you don't need to run 5 epo in a full training, right? You only need to run a few steps. For example, I would say 10 to 20 steps to see how it performs, and then you can iterate to that and do the optimization. And then when you have the final config that you're confident that this is the best in this case, then you can start the full pipeline for the training with a full data set, because the full data set with the optimization will take 2 hours. So we expect you to be able to bring it down to anything between perhaps 30 to 60 minutes, depending on the optimization. But please start with the small steps and then only do the full training with the final optimal config that you have. So for the report, please keep it short, 500 word maximum. We prefer quality over quantity. You can include some of the picture from your logs or your profiling. We will render it to the PDF later, but please include it in the submission as well. So that's all information we have for the task. So let us know if you have any question now, or you always can reach out to us by Slack.
So there was a question from the FAU team about a little bit about the task, the AI task that we have for them about the llama. Can you say a few words about that?
So yeah, so the question is, there is no. So the question is whether on the on-site for the on-site competition we will have anything different than Llama CPP, like maybe max text. Answer is no. For virtual only, max text is the competition has max text, and for on-site we will only have Llama CPP. The details or more information for which we will provide a little bit later. But max text only for virtual, Llama CPP only for on-site.
Yeah. And for Llama CPP, please go ahead with information that available on the repo. You can already try to run it on your cluster, make sure it's working, and maybe play a bit with different flag and configuration.
Okay. Anyone, any additional questions? Just feel free to say or to write on the chat if needed. It could be overwhelming in the first day, so I'm not sure if you have so many questions, but please use the Slack, please use the team channel for specific questions, and we'll try to help you as much as we can. Okay, I don't see any additional questions. Okay. Okay.
So, yeah, there's one question over here. So
Yeah.
how similar will the Llama CPP task be to MaxText? Would be fine-tuning specifically or inference? So it will be inference only.
So just in general, for the on-site part, it's very dense. It's very packed. We don't have a lot of time. So we try the task to be shorter. And I mean, we won't ask you to write reports and all that. So, you know, it's slightly different. The virtual task is longer, is about a month and a half. So the teams, they have more time to evaluate, debug, run, write reports, and all that. So slightly different approaches.
Oh, yeah. I mean, if you are interested in trying the MaxText task just for educational purpose, right? Just to learn. So if your team cluster have NVIDIA GPU or even AMD GPU, you always can try it on your cluster. So So in the instruction, we actually provide you with a container that work on any NVIDIA GPUs. And I believe that AMD also have similar container that build for their GPUs as well. So I think you should be able to launch MATEX on your local machine just to learn. And I actually put quite detailed information on how you can convert the model weight by yourself there so that it fit into MATEX input format. The only thing missing will be the data set. So if you're interested in trying, I also can give you either the full data set or the partial data set so that you can try and learn.
I will add that we will not grade that for the on-site teams. You will have another task. But if you want, again, we can you know, if you want to experiment with that, we can try to help, as Phuong mentioned.
Yeah. So for the Llama, it included. So
there is another question in the chat. They're asking if the on-site task will include Llama Bench or something else. Yes, Llama CPP has a lot of different utilities. Llama Bench, Bash Bench, Perplexity. So the task would include any or all of these. As we said, more information coming soon.
Yeah, so we will try to publish more information next week, right? And then part of the information will be published next week, and the final pieces of the info will be published at the competition.
Yeah, we are planning to publish the actual task during the competition. Maybe a little bit.
So we will provide you some info so that you can practice and prepare at home, but the full detail about the model and what we are looking for and how do we rate it, we will give you more detail at the competition.
Yeah, if anyone has any question related to max text, the virtual tasks, how to use the cluster, please ask that now.
On Slack.
On Slack.
Yeah. So again, start trying that. See that you got access to Romeo. If you have any issues with the cluster on Romeo, let me or Arnaud know, and I'll try to help you with that. You will have one user per team, and just go ahead and start using. Most of the time you have the cluster, so it's about a month and a half. So try to utilize the time. Don't wait for the last week or two, because I know how working is, say, oh, well, you just push everything to the last minute. Don't do it. It will be packed. You won't have resources. Just start now. Okay. And again, if you have questions later on or as you go, reach us, and we'll try to help. Okay. Okay, so thank you, everyone, and we'll see you tomorrow. We'll have tomorrow at 8 a.m. Pacific time the ASCOT 5, and following by the HIMDB and OpenFOAM later on. So look for that on the agenda page, and join us for that. Okay, and I will publish the video later on the wiki pages. Okay. Okay. Bye bye, everyone.
Thank you. Bye bye.
Bye bye. Thank you, Phuong and Sudha.